We're very proud to be part of the festival and congratulate the Beautiful Science Foundation on this excellent annual event. Science, technology, engineering, and math benefit all of us. Through them, we find solutions to complex challenges, and they provide inspiration for the innovators of tomorrow and today. Tonight, I have the honor of introducing one extraordinary innovator. Dr. Dominic Pеши is an astrophysicist for the Event Horizon telescope at the Harvard-Smitsonian Center for Astrophysics. It's a lot of big words. Dr. Pешi and his team made news around the world when they produced the first directly observed image of a black hole. Imagine that, the first image of a black hole. It's such an honor to have Dr. Pешi join us, and I personally cannot wait to hear all about his groundbreaking research. And now, please welcome Dr. Pешi.
Thank you, Mike. Get the screen share going here. So hello, everybody. As Mike said, my name is Dominic Pешi. I go by Dom. And I'm a radio astronomer studying black holes as part of the Event Horizon telescope collaboration. And today I'm going to be telling you about how we went about taking the first picture of a black hole. So if you get up very early tomorrow morning and you look east towards the rising sun, there in the sky between the constellations of Virgo and Leo lives a distant group of galaxies. It's a galaxy cluster called the Virgo cluster. The largest galaxy in this cluster is known as Messier 87, or M87 for short. And shooting out from the center of this galaxy is an enormous relativistic jet, many thousands of light years in length. And the source of this jet, the origin, sitting in the very heart of this galaxy, is a supermassive black hole weighing 6.5 billion times as much as the sun. And this black hole, which is known as M87 star, is the very first that mankind has ever taken a picture of. And so today, I'm going to try to tell you some of the story behind how this picture that you're seeing on the screen right now came to be. But first, let's start with a somewhat simpler question, which is what even is a black hole? So I posed this question to some online dictionaries just to see what they thought. I got several different answers. But there were some common threads in these answers. So some of the dictionaries indicated that black holes are theoretical objects. So there's a question of whether they even exist. Some of the dictionaries weren't sure whether black holes were objects or whether they were regions. Are they something kind of physical, tangible, or are they a location? Some dictionaries thought that perhaps the genesis of a black hole, that it may be formed from collapsed stars, was its key defining feature. But all of them agreed, all of these dictionaries agreed that something important about a black hole is that nothing can escape from it. And it's this last property that I feel is truly the most important thing to know about black holes. A black hole is a concentration of mass that is so compact that its gravity prevents anything from escaping its pull. And a useful concept for capturing just how gravitationally powerful any object is something called its escape velocity. The escape velocity of an object is exactly what it sounds like. It's the velocity at which you would need to be traveling in order to completely escape the gravitational pull from the surface of that object. And so over the next few slides, I'm going to run through the escape velocities of some well-known objects that all of you know about. But just for reference, I will let you know, and this is a bit of a confession, that my own personal escape velocity is about 0.1 millimeters per second. So I'm looking to lose a little weight in the future. But okay, so for objects that are a little more familiar to all of you, this is the moon, and here's my little cartoon rocket over here. And so the question is, what is the escape velocity from the moon? It's the measure of the moon's gravitational power. Well, it turns out that the escape velocity from the moon is a bit less than 2.5 kilometers per second. That's pretty fast. I mean, a kilometer per second is already a very fast speed. 2.5 kilometers per second is faster than the fastest plane that's ever been built, and it's faster even than bullets shot from a gun. Fastest bullet on the market is less than 2.4 kilometers per second speed. So when the astronauts who landed on the moon wanted to leave it and come back to Earth, They had to launch from the surface at a speed of about 2.5 kilometers per second just to leave. All right, here's another object I hope everybody's familiar with. What about the Earth? What's the escape velocity from the Earth? It's something that rockets launched from the Earth have to all the time overcome. And it turns out that the escape velocity from the surface of the Earth is about 11 kilometers per second. It's higher than the escape velocity for the Moon because the Earth is more massive than the Moon. It has stronger gravity. And this is my favorite, largest planet in the solar system, Jupiter. It's even more massive than the Earth, so its escape velocity is even higher, about 60 kilometers per second. These are already numbers that we really don't experience on Earth, these sorts of large speeds. And then the Sun, of course, even more massive still than Jupiter, with an escape velocity of over 600 kilometers per second. So we're seeing this trend. As you increase the mass of the object, as it has more weight, the escape velocity from it increases. And that makes a lot of sense. We think of gravity as something that cares about the mass of an object. If you have something more massive, it is more gravitationally powerful. And this measure, escape velocity, is capturing that intuition. But increasing the mass of an object is not the only way to increase its escape velocity. The other way to do so is to keep an object having the same mass, but then pack it into a smaller region of space, thereby increasing the density of the object. And so if we were to take the Earth and squish it down by a factor of 100, such that it was only about 130 kilometers across, then its escape velocity would increase from 11 to about 110 kilometers per second. So that's faster even than the escape velocity from Jupiter, though it's not quite as fast as the escape velocity from the Sun. And that's without changing the mass. And that's because mass is not the only concern here. It also depends how close you can get to the mass. Remember, the escape velocity is something that's defined to be from the surface of an object. So if you can pack more mass into a smaller region, you can increase, or sorry, the same amount of mass into a smaller region, you can increase the escape velocity correspondingly. And if we were to squish the Earth even more by a factor of 1,000,000, then it would only be 13 meters across. And if we did that, the escape velocity from the Earth would be over 11,000 kilometers per second. This is much faster even than the escape velocity from the Sun. But again, this is without changing the mass of the Earth. But in principle, we can imagine going even further. If we could squish the Earth down by a ridiculous factor, 720 million, then the Earth would be less than 2 centimeters across, the entire mass of the Earth in a region less than 2 centimeters across. And at that point, the escape velocity would be about 300,000 kilometers per second. The density of this tiny Earth at this point is enormous. And this 300,000 kilometers per second value is actually a very special value because it is the fastest speed that anything in our universe can travel at. 300,000 kilometers per second is the speed of light. And so that means that even something traveling at the fastest possible speed would no longer be able to escape from the surface of this super squished Earth. And if you can't escape from something, even when traveling at the fastest possible speed, then that means that you can't escape from it at all. Which means that at this point, we would have turned the Earth into a black hole. And that's really the key defining feature that I want you all to remember for what makes a black hole special. A black hole is what happens when you take some amount of mass and you pack it into a sufficiently tiny volume such that to escape from the gravitational pull of this region, you would need to move faster than the speed of light. And because nothing can do that, nothing can move faster than the speed of light, that means that once anything falls into a black hole, it can never get out. It's gone forever. And this is the conception of a black hole that I think is important to have in your head. And there are three individuals, three important figures in the history of black holes that I think are worth mentioning. The first one is this fellow John Mitchell, who is an English clergyman and philosopher. And he was really the first person to publish the idea of black holes. Long before the sort of theories of gravity that we have now were established, he conceived of these objects, which he called dark stars at the time. And he recognized that if there could exist an object that was so gravitationally powerful that even light couldn't escape from it, then we would not be able to see that object in any traditional sense, because we use light to see things. The next individual I'd like to highlight is Carl Schwarzschild, a German scientist whose black hole solution was the first full solution to Einstein's famous field equations of gravity. And Karl Schwarzschild famously sent a letter containing his solution to Einstein while Schwarzschild himself was serving in the army on the Eastern Front during World War I. His solution was published in 1916, and Karl Schwarzschild died the following year from medical issues that he contracted during the war. And then, of course, the last individual is one who needs very little introduction, Albert Einstein himself. His theories of both special and general relativity still underpin our modern theoretical understanding of black holes. But all right, that's it for history. Hopefully we have now some sense of what a black hole is, but we still have a question of what it means to see one, and even what we might expect one to look like. And it's a fact that's worth noting that even though black holes themselves don't emit light, they do have a very strong, and it turns out very characteristic effect on any light that passes sufficiently nearby them. And so in this video, this is a cartoon animation, you're watching light rays that are passing near a black hole, and you see their trajectories getting bent by the black hole's strong gravity. And then as we pan the camera and we look at this black hole from very far away, we can see that this bending of the light rays around the black hole has the effect of deflecting all of the light from a certain region around the black hole when you're looking at it. This central dark region here is something we refer to as the shadow of the black hole. And it's this black hole shadow that we can actually observe. If anything near the black hole is emitting, then we can watch for this region of no emission and use it to identify the black hole. And the first person to mathematically describe this general appearance of the black hole shadow was James Bardeen, a physics professor emeritus at the University of Washington, who actually just passed away earlier this year. And he derived this general expression in the early 1970s and had an interesting quote up here on the screen that I think is worth taking a moment to appreciate, because he said, "It is conceptually interesting, if not astrophysically very important, to calculate this precise shape. But unfortunately, at the time, there seems to be no hope of observing this effect." And there's a reason for that. It's because it's very challenging. But before I talk about the challenges, I just want to note that those initial calculations were supported by later numerical simulations. And here's showing some snapshots of the history of the theoretical understanding of what a black hole might look like. Jean-Pierre Luminet in 1979, Heino Falke and the collaborators in 2000, Thomas Brunswick more recently in 2018. People have been simulating these things, and all of these simulations show this characteristic feature predicted by Einstein's theory, that the black hole should exhibit a shadow in the center of any emitting material around it. But okay, so what is that challenge? Why was it that Dr. Bardeen thought we would never observe this effect, even though it's predicted to be there? And it's because we still have a problem that we need to overcome. Black holes, despite being some of the most massive objects in the universe, are actually really, really tiny. And what do I mean by that? So I mean this in an angular sense, meaning how much of your field of view does the black holes fill up, or what fraction of the night sky does a black hole subtend? And in units that may not be super familiar, but in units that you've come across, I'm sure, the supermassive black hole in the M87 galaxy that I mentioned earlier is only about 10 billionths of a degree across. So how small is that? Well, 10 billionths of a degree is about the same size as the smallest text that would be written on a newspaper that if you're looking at it from several thousand kilometers away. So if I had a newspaper here, and I unfortunately don't, it would have been a nice prop. But if I had a newspaper here, I'm in Boston right now, in Massachusetts. In order to be able to have good enough resolution to see a black hole, that would be equivalent to you over there in Sofia, being able to read my newspaper from where you're sitting. So it's kind of ridiculous. But there are other analogies we could make and that people like to make, so I just want to run through a couple of them. 10 billionths of a degree across is also about the size that a donut would have if it were sitting on the moon and you were looking at it from Earth. And this one's my favorite. 10 billionths of a degree. So I do have one prop with me today. I have in my hand an atom. You can't see it because it's really small, but I have it. And if I hold this atom at arm's length, about 1 meter away from my face, the size of that atom in my field of view is about the same size as the black hole in M87 in the night sky. This is all just a way to impress upon you the fact that these are really tiny. You really have a hard time seeing. You need very specialized equipment to do it. So how do we go about taking a picture with fine enough angular resolution to see such a tiny object? And it comes down to what limits our resolution, which is an optical effect called diffraction. And this is the same effect actually that lets you hear around corners, even though you can't see around them. And so we actually take advantage of diffraction every day. But for our purposes, for the astronomical purposes that we're looking here, the diffraction of light actually sets a limit on how tiny of an object we can see with our telescope. The size of the smallest details that our telescope can see is given by this ratio of the wavelength of light that we're observing at to the diameter of our telescope. So these are the two numbers we can play with in order to try to get better angular resolution. Let's first try to play with the wavelength. This is a graph. I promise it's the only one I'll show. It's a very crude graph that shows the amount of light coming from M87 as a function of the wavelength of that light. So here we have 1 micrometer, about 1,000 times smaller than a millimeter. Here we have 1 millimeter. You're familiar with a millimeter? And here we have 1 meter, right? So this is a scale spanning many ranges, but this line is showing intensity increases for a bit and then decreases for a bit. And so the amount of light, the largest amount of light that we can get from this object is emitted at a wavelength of about 1 millimeter. So that seems like a reasonable candidate for the observing wavelength that we'd like to pursue. Because after all, the brighter the source is, the easier it will be to see. But you have to remember that we'd be able to see smaller details if our wavelength was smaller. That's what this equation is saying. So maybe we'd be better off considering some somewhat shorter wavelengths, a bit toward the left here, even though there's a bit less light. Maybe that would be advantageous. But unfortunately, it turns out that the Earth's atmosphere is not cooperative. At the wavelength shorter than a millimeter, there's actually atmosphere in the way. So the Earth's atmosphere absorbs light at various wavelengths. And it turns out that the Earth's atmosphere is blocking much of the light shorter than 1 millimeter. And so that turns out to not really be an option for us. And we're stuck with this 1 millimeter observing wavelength. But what about the second part of this expression? The size of our telescope appears in the denominator of this expression, which means that we have a larger telescope than we would be able to, in principle, see smaller details. So the question becomes, how big of a telescope could we possibly build? Could we make a telescope the size of the entire Earth? If we could, we'd have a telescope with a diameter of about 13,000 kilometers. So let's suppose that we could do that. Plug that into our equation, and we find that the smallest details we'd be able to see are about 5 billionths of a degree across. And remember that the size of the black hole we'd like to look at is about 10 billionths of a degree across. This coincidence, the fact that we can, with the wavelengths we're able to observe at, and the biggest telescope we could possibly build, just barely resolve the largest black holes in the sky, has been called a cosmic conspiracy. It just so happens that from the Earth, we can just barely achieve the necessary angular resolution to take a picture of a black hole. We can just barely do it, but we can do it. And so, we have assembled the Event Horizon telescope. Now, of course, we can't actually build a single telescope the size of the Earth, but we can connect up multiple smaller telescopes distributed around the globe to act as one single large telescope. So we have 2 telescopes located on Mauna Kea, a dormant volcano on the big island of Hawaii. It's actually not too dormant, sometimes still erupts. One of these telescopes is itself a little group of telescopes called the submillimeter array, while the other one is called the James Clerk Maxwell telescope. We have one telescope on top of Mount Graham in Arizona. This telescope is called the submillimeter telescope. We have another telescope located on top of the Sierra Negra, which is an actually dormant volcano in Mexico. This telescope is known as the large millimeter telescope. We have another 2 telescopes situated in the Atacama Desert atop the Chajnantor Plateau in the Andean mountains of Chile. One of these is another group of telescopes known as the Atacama Large Millimeter / Submillimeter Array, and the other one's a standalone dish known as the Atacama Pathfinder Experiment. We have a telescope located on Pico Veleta near Granada, Spain. And this telescope is run by an institute whose name I have a hard time pronouncing, the Institut de Radio-Astronomie Millimétrique. Apologies for those who are French. And it's known as the IRAM 30-meter telescope. And then finally, we have one telescope located in the South Pole, which is known very appropriately as the South Pole Telescope. But this one, it turns out, can't actually see M87 because it's located too far south, and M87 is in the northern hemisphere. But the South Pole Telescope is part of the array, and it does participate in other observations with the rest of the telescopes. All right, so that's a lot of names, I know. And many of them are very similar sounding, millimeter this and sub-millimeter that. And so within the Event Horizon Telescope collaboration, which we call the EHT, it's very common for us to use abbreviations to refer to these telescopes, and even to refer to the collaboration itself, like I said, with an abbreviation, the EHT. So I'll try not to use too many of these abbreviations today, but if I do accidentally say something like SMA or LMT, then at least you'll have some idea what I'm talking about. These are just the abbreviations we use for these various telescopes. Now, because the Event Horizon Telescope is not really one single telescope, but is instead made up of all of these many telescopes that I just walked through, we need to use a special technique to combine the signals from all of these separate telescopes. The technique that the EHT uses is called interferometry. And I really don't have time to go into the details of it here. It's a whole college-level lecture course by itself. And things can get very technical very quickly with interferometry. It's a technical field. But the basics of it, the fundamental measurements that the EHT makes, ends up coming from pairs of telescopes rather than individual telescopes. It turns out that when you use this technique called interferometry, you need two things to interfere one with the other. And so it relies on pairs of telescopes. You can't carry it out with any single telescope. So each pair of telescopes, like I'm showing here on the left, contributes a data point to this, what I'll call a virtual mirror here on the right. This is the space we're going to use to collect our data and ultimately recover an image. So that's a data point that we get from one pair of telescopes. And there are technical reasons why we actually get a second data point for free for every pair of telescopes because of some nice mathematical property. But that's really a detail. The point is that we get data points associated with each pair of telescopes. And another point that I'd like to emphasize is that this telescope here on the right, this virtual mirror here on the right, is, we have a pair of telescopes on the Earth, and you can see that there's this big circle of the mirror that we'd like to have filled in with data. But even if we only have a handful of telescopes on the globe, they can only fill in a few spots over here on the right. They can never fill in the whole thing. And so the way we try to get around this and fill in the mirror more fully is by taking advantage of the fact that the Earth rotates. And when it does so, and I'll play in a moment how the Earth rotation looks when viewed from M87, when we do that, the locations of the telescopes on the globe move as seen by the source. They aren't moving on the ground, but the apparent motion induced by the Earth's rotation actually causes the data points that we have in the virtual mirror to also move in this space. So here's what that looks like. As the Earth turns, telescopes come into view, and new pairs of telescopes are arriving, and we fill in some amount this virtual mirror here on the right with new data points. We're just staring at the source. All of the telescopes are looking at the same M87 source. And now you see when we're over East Asia and the Pacific Ocean, we don't have a lot of telescopes in that region, so we don't see anything. But as the Earth rotates back around, you'll watch the European and Chilean telescopes connect up, and then the North American telescopes will connect up again. This video will loop. And so this is how we fill in areas of this virtual mirror that otherwise we wouldn't have access to. We take advantage of the Earth rotating like this. Here's the sort of fullest kind of coverage that we can get. But even after allowing for this Earth rotation effect and taking advantage of that, you can see that these blue regions here on the right still don't fill in the entire circle. There are still a lot of gaps remaining in our data. And so here's where we have to use special computational techniques to fill in those gaps, to interpolate into the regions where we do not have any data. And I'm going to talk more about how we do that in a bit. But first, I just wanted to quickly show you the journey that our data take. So we collect them at these telescopes, and from those telescopes, they need to undergo a long process before making their way to our computers. And I want to sort of share that with you. The very first thing I'd like to point out is that the volume of data we collect is extremely large. So here are some images showing actual observing teams at several of the telescopes during our 2017 observing campaign, which is our inaugural observing campaign for the Event Horizon telescope. And across several nights of observing over about 10 days, we collected a few petabytes worth of data. So the raw signals are on the petabyte scale. And for reference, most of the files that you probably work with on your computer are maybe kilobytes or megabytes in size, with the largest files being maybe a few gigabytes. That's really the largest we tend to work with computers, sort of personal computers on a daily basis. And so gigabytes is kind of the largest size that we tend to encounter. And then a terabyte is 1,000 gigabytes, and that's comparable to the size of everything that your computer is able to store, is on the order of a terabyte. And then a petabyte is 1,000 terabytes. So you can imagine 1,000 personal computers worth of information in 1 petabyte. And we collect several of those over the course of just a couple of nights here. So we're really collecting a huge volume of data. And it turns out that when you have that much data, you can't actually transfer it over the internet. It would be much too slow. Emailing this or putting it in some sort of shared folder would never work. We can't transport it. It turns out that the highest bandwidth data transport that we can provide is in literally shipping crates full of hard drives manually from each telescope to the central computing facility they need to go to. And that's what you're seeing here. This is a fellow, Don Souza, who's packing up one of these crates full of hard drives for shipment. He's actually unpacking it. It just got shipped. But the idea, you see these crates, these sort of meter-cubed crates that we actually send the hard drives in. And that's the most effective way to transport this volume of data. The internet doesn't cut it. The facility that the data go to houses a supercomputer called a correlator. And it's in this supercomputer that the data undergo their first round of processing. So in the correlator, the data from individual telescopes are played back synchronously, and then they are aligned. Each of the data streams from the individual telescopes are aligned so as to simulate an observation with a single large telescope the size of the Earth. And during this process, there's a lot of averaging that occurs. So the data volume gets reduced by about a factor of 1,000, bringing it down from petabytes to terabytes. And this picture here is showing some of the EHT scientists and engineers at the correlator facility here in Haystack, Massachusetts. So after the data have been correlated, they need to be calibrated. And this turns out to be a very time and labor-intensive process that involves precise tracking and removal of a very large number of effects that come from the atmosphere above each telescope and the back-end electronics that the data have traveled through, all of these corrupting effects. And the calibration team, which is this image here, removes all of these effects, permitting a large amount of additional averaging, and at the end of it all, bringing the total data volume down from the terabyte level to the megabyte level, which is something much more familiar with and which we can work with on our computers. And from there, we carry out image reconstruction. So after that pathway, the data have been sufficiently calibrated that we can then reconstruct an image from the data. And in a moment, I'll say a bit more about that. But first, this photo here, I want to point out, was taken in 2018 at an EHT imaging workshop. This was before the results were published, but it was after we had achieved them internally. So this was actually the time when the black hole image was first reconstructed and revealed to the team. And you can see in the background of the image here an early version of the picture of the black hole that you know now a bit more familiarity with. But okay, on to the last bit, image reconstruction. So remember that when we collected the data, there were many gaps in our virtual mirror. And that incomplete information means that there actually is no unique image that can explain the data that we collect. There are an infinite number of images that our data can describe. And so to narrow down the possibilities from infinity to something finite, we have to impose certain constraints on the sorts of images that are permissible. And we try to be very conservative in the sorts of constraints that we impose, such as that the image cannot have a negative amount of light, or that the structures in it must be somewhat smooth and continuous. But while these sorts of constraints do help to narrow down the kinds of images that are possible, they don't uniquely select a best image. And because our algorithms, our computer tools, they need to be run by people, we were worried when we were making this image that we might be introducing biases ourselves when using our tools to reconstruct the image, because there's not a unique image. And so to minimize these sorts of human-introduced biases, once we got the M87 data in that workshop in 2018, we split up into 4 different imaging teams that each undertook the imaging entirely separately. And these are the institutions that participated in each of the 4 teams. And these were selected approximately to have convenient geographic locations, everybody's located in a similar place, and also because the members of each team were using a similar software to reconstruct images. And each of these teams carried out the imaging process without talking to anybody from any of the other teams. And altogether, we spent 7 weeks working on the data in that fashion. And then after 7 weeks, all of the teams got together and compared their images. And this is what we found. Note that these images from each of the teams do not look exactly alike. Because remember that there are a lot of assumptions that go into the imaging algorithms to produce a single image from these imperfect, incomplete data. So different choices about what assumptions to make result in slightly different images from one team to the next. But importantly, all of the images share some critical similarities. The most apparent similarity is the presence of an asymmetric, ring-like structure surrounding a darker central region. And this ring is the same size in all of the image, and the dark region in the middle is the black hole shadow that we're after. And now there's additional processing to determine the final image for the entire collaboration, and we moved beyond the human-driven imaging approach for that and automated the entire procedure. A variety of synthetic datasets, fake simulated datasets were generated to train the parameters of our imaging algorithms. And then these trained and automated algorithms were applied to the real M87 data to produce an image that was entirely free of human intervention. The images across all of the reconstruction softwares and all of the datasets were processed to achieve the same resolution. And then they were all averaged together to produce a final, maximally conservative image that captures only the structures in this image that we think are most believable and does its best to average away, smooth over all of the structures we think may be spurious or hard to believe or an artifact of the image reconstruction procedure. So that's it for the image reconstruction procedure. That's it for imaging. But in the last couple of minutes here, I'd like to just point out that imaging, taking this picture of the black hole, taking these data and making this image, was not the only analysis that we carry out on the EHT data. That's just one of many. A big part of EHT science is producing state-of-the-art simulations of how these black holes should look, which allows us to make predictions, physical predictions, about what sorts of features in the image map to different kinds of physics in this material that's accreting onto the black hole. And then, of course, we also fit other kinds of models to the data as well. For instance, geometric models, like I'm showing you on the screen here, that we use to extract quantitative measurements of properties, like the size and the shape of the emissions region. So we see this image. We'd like to know how big across the ring is. That turns out to map onto the mass of the black hole. We'd like to know how it's oriented. That turns out to be important for understanding the direction that the black hole is spinning in. These sorts of measurements need to be made from the data. We have models for doing that. And then, of course, M87 is no longer even the only black hole that we've made an image of. Just earlier this year, the Event Horizon Telescope collaboration released the first image of the black hole in the center of the Milky Way galaxy, our own galaxy. This black hole is called Sagittarius A star, or Sag A star for short. And I'm showing that image here, which was produced using a method that was very similar in spirit to how the M87 image was produced. But there were a number of updates and modifications that had to be made to accommodate some special difficulties with Sag A star. That's really an entirely separate talk. And then finally, I'd just like to emphasize that the EHT collaboration is really that. It's really a global collaboration consisting of a couple hundred scientists distributed in many countries around the globe. And so the Event Horizon Telescope, in addition to being a globe-spanning network of radio dishes, is also a globe-spanning network of people. And really, this is a global effort in just every way. And with that, I've reached the end of my talk. So thank you all for listening.
Hi, hello. Great presentation. Thank you. It was very interesting. And I have a bit of a more hypothetical question, but if you have two quantumly entangled photons, and one of them is in the black hole, the other one is outside of the black hole, we somehow view the one inside of the black hole, and we know its spin. Doesn't that mean the other one has also a determined spin, and that information has escaped the event horizon, technically?
So, okay. This is a very technical question that you're asking. So you're asking, let me make sure I understand the question properly. You're asking about, and you're talking about spin of photons now, is that right? You're talking about the angular momentum of photons when you say spin here. Yes. So you're asking if you set up, so apologies for almost everybody in the audience for whom this may be very unfamiliar, but you're asking if you set up a system in which you have two photons that you've initially coupled in a quantum mechanical way known as entanglement, and then you allow those photons to propagate in different directions. One of them enters the black hole, the other one exits the black hole, or the other one is somehow outside of the black hole. And then you measure some property of the one outside of the black hole. The active entanglement has given you information about the one inside the black hole. And you're asking, has not information escaped the black hole in this manner?
Yes, that's exactly the question.
So I think, and I should preface this by saying I'm not a quantum gravity expert, so this is not necessarily my area. But my sense is that no, entanglement encodes all of the information in the same amount of information in both photons. So a measurement of one photon entirely contains the information that's in the set of two photons. That's what the active entanglement prevents. And so if you make a measurement of one photon, all of the information is there, and there's only redundant information in the other one. So the information has basically been duplicated. So I don't think there's any information escaped from a black hole that occurs by encoding some information in entangled photons in this way. There are quantum gravity ways to extract information from a black hole using something called Hawking radiation. It's all very hypothetical, but it's not something that I think you can set up in exactly the way that you've described here. It's a process that needs to occur really in the immediate vicinity of the black hole horizon, and due to the fact that there are, in this particular theory, the black hole is itself a quantum mechanical object. Less so that you just have a quantum mechanical object entering a classical black hole. I'm not sure if that's really answered your question, but I think the short version of my answer would be no. That doesn't violate some sort of information paradox.
Thank you.
Hi, thank you for the lecture. I have a question. Most of the telescopes that we work with are based in the Americas, and we have one in Europe. How would affect the whole research that you guys do as a scientist if we had telescopes also based in Asia and in Australia? Would that significantly improve your work?
This is a great question. This is asking about, how can we leverage the fact that right now the way the Event Horizon Telescope has worked, just so you know how the telescopes were selected as part of the array. These telescopes, all of the ones I mentioned, were existing before the Event Horizon Telescope collaboration was built. The collaboration is just an agreement among all of these facilities to observe together in this unified way so as to make these kinds of images. So we didn't purpose build any of these telescopes. And if we had done so, we may have distributed them more evenly around the globe. We were just using what existed. But that's not quite the answer to your question. That's just a little bit of history. Part of the reason that we can't just go anywhere, we can't just put a telescope wherever we'd like, is because of that atmospheric effect I mentioned a little bit during my talk, the fact that the atmosphere blocks some of the light from these objects. It turns out that there are only a few places in the world, the very highest and driest locations on the tops of tall mountains in very dry locations, where we can even make these observations in the first place. A 1 millimeter observing wavelength is in many places on the Earth not observable. If you were to build a telescope here where I am in the city of Boston in Massachusetts, it would never work. It wouldn't work at all because the atmosphere would entirely block all of that light. You need to go higher to get above much of the contaminating, it turns out, water vapor in the atmosphere before you can actually get enough light coming through that you can detect it. And so there are some places in East Asia. There's some locations in Tibet, for instance. There's some locations in Japan. There is sort of like Mount Fuji. There aren't too many places in Australia. The Antarctic continent is a very nice place for it. Turns out being very cold removes a lot of the water vapor from the atmosphere. And there are additional places in South America, and actually in Africa, there are a few places. Mount Kilimanjaro in Africa is one of the places where we don't currently have a telescope, but which would be appropriate for these kinds of observations. And we're aware of these things. And in fact, there's an effort known as currently the next generation Event Horizon Telescope that is actively looking to put new telescopes in places around the globe so as to enhance the array. And you're absolutely right. If we could add more dishes to the array, particularly in places where we don't currently have any, then those dishes would form pairs with the other existing dishes. And they would add many more data points to the virtual mirror I was talking about. And that would fill in the gaps much more thoroughly. And that's in fact exactly the goal. The more telescopes you add and the more locations, the more comprehensively you can fill in this aperture that we're just really approximating. But the closer we can get with more telescopes to not having to approximate things, and the more precisely we can pull out and more definitively we can pull out the image structures and be able to have something maybe not quite as blurry as these things, but a bit more detailed. And in fact, with enough telescopes, we don't even need to wait for the Earth to rotate. We can get an image just in one instant, and then we can wait and then get an image in the next instant. And we can wait and get an image in even the next instant and build up a sequence of images in time. And what is a sequence of images in time but a movie, right? So that's actually the goal, that one of the driving goals of the next generation Event Horizon Telescope is to put enough new dishes on the ground around the world so that we can make movies of these black holes, not just still images.
Great, thank you. So there's a project, existing project that's...
There's an existing project that is working on exactly this question.
Thank you.
Hello. My question is, if the light travels near the black hole, wouldn't the black hole gravity affect the light itself and split it in different wavelengths and making it in different colors? And by that I mean the different colors have different, I assume, different speed. So maybe the trajectory of the lights of the different colors will that create like a rainbow pattern near the area of the black hole?
Okay, so there are a couple of points here that I'm going to touch on in your question. One is this effect that the gravity of the black hole has on the wavelength of the light. So I wouldn't say that it splits the light. So you think of light as being many, we think of light in physics as being composed of individual photons. We call them the smallest parcel of light that you can have. And individual photons don't split. Their wavelength can change by the gravity of the black hole. So if you're very close to the black hole and you emit a photon of light, its wavelength at emission will be different from the wavelength that gets observed very far away, because the black hole will effectively stretch out the light due to its gravity. And so the wavelength will increase, it will get longer, and longer wavelength light has lower energy. So you think of it as like energy was lost in this process of escaping from the black hole. But it's not the case that the light changes speed as a function of its wavelength. The wavelength of light and the speed of light, they aren't really connected in that way. The speed of light is the same no matter what wavelength of light you're looking at. So if I'm looking at radio light, like 1 millimeter, like we tend to look at for these black holes, then that has the speed of light. And if I look at light that I can see with my eyes, I can't see 1 millimeter photons, but I can see photons of wavelength about 500 nanometers. That's like green light for us. That has the same speed. And if I look even shorter wavelengths at X-rays, right, or gamma ray light, it all has the same speed. The speed of light is not dependent on the wavelength of the light. So it doesn't affect the speed, but it does, you're right that it does, and it does affect the effective color, meaning the wavelength maps to the color. And so the light being emitted very close to the black hole is much more heavily, what we say, red shifted. It is much more heavily pushed to longer wavelengths than light emitted a little further out from the black hole, or even a little further out from that. And all of those effects are actually accounted for in our predictions for what the appearance of these objects should look like. And in fact, that heavy red shifting of the light is in part responsible for that very dark region in the middle. And that's just because any light that is kind of emitted very close to the black hole there is so heavily drained of energy that you don't expect to see it at all. Whereas light that's emitted in somewhat other directions or somewhat other regions gets less heavily drained of energy, gets less heavily red shifted, and therefore we can see it. But yeah, by looking at different frequencies, we expect the structure of the black hole as we see it to change a little bit, the structure of the emission region around the black hole. And that's partly because of this gravitational red shifting effect. So tried to answer your question. I'm not sure I really quite got it, but this effect absolutely happens. It absolutely impacts the image of the black hole, and we account for it. It's not quite a rainbow pattern, just because we don't see these light waves. Like all of the color you're seeing in these images is artificial, right? We sort of color it just so that we can look at it with our eyes, but really the light that's being emitted is at wavelengths that our eyes cannot see. So there's not really a rainbow in the traditional sense, but there's a range of colors, a range of wavelengths.
Thank you.
Thank you, Dom, for the excellent presentation. I'm now going to put you on a little bit of a spot into career mode, career advice mode. So there are a lot of younger people here who are very engaged in your talk. Mm-hmm. What could they be doing now to become part of the next generation project and be up on the stage telling everybody about how they made the first movie of a black hole? Yeah,
this is a great question. So younger people of all ages, right? So I'm not sure what the career stage we're talking about is here. Folks in high school, folks in college, folks in graduate school. I think if you're a student looking to study these kinds of objects, then the things you should be getting involved in are well, I would say there's several categories. It depends on what exactly you'd like. There's pathways that are excellent for engineers, right? If you like to build things, if you like to put together hardware or be involved in putting together telescopes, there's pathways there where if you are somebody who's really into the sort of mechanical engineering side of things or the digital signal processing side of things, we use all of that. We have a number of engineers in our collaboration who are sort of just experts in all these areas, and we're constantly looking to push the frontiers and build, for instance, receivers that can detect light at even higher frequencies, at even shorter wavelengths than the ones we've observed here. And doing interferometry at those wavelengths is a sort of technological frontier that hasn't yet been done. And so that's almost entirely an engineering problem, getting sufficient sensitivity to detect these things reliably, getting sufficient stability in your instrument, to be able to track the timestamps that we have to put on these things are at the nanosecond level. It's extremely technologically demanding. Engineering is a huge area. Physics, of course, on the science front, physics and astronomy are fields that we pull from just enormously, and even mathematics and statistics in our data analysis. And so we have people who are experts in numerical relativity. They perform simulations of the accretion around these black holes. There are people who are experts in what I would call pen and paper relativity. They think about how the actual space-time around these objects could be altered if Einstein's theory wasn't quite right, and how can we test that using our observations? How can we really ascertain that what we're looking at is what Einstein predicted? There are people who are much more into the sort of maybe more astrophysical side of things. The material itself that's accreting onto the black hole is a plasma, billions of degrees, and it's falling at nearly the speed of light onto this object, and it's heating up so enormously and emitting what we call synchrotron radiation. All of these processes are physical processes, astrophysical processes, that people have to sort of work through for a given temperature, for a given composition of plasma. What should the emission look like in order to understand how we would expect a particular emitting material to look, so that when we actually look at these black holes, we can say, are we seeing a pure electron plasma? Are we seeing a plasma that's made of electrons and positrons? What exactly are we looking at? That depends on the specific nature of the emission of this material. And plasma physics is, of course, a big open area with lots of contributions to be made. And then down even of that, there's the data analysis side. We collect these huge volumes of data, correlate them, calibrate them, reduce them into sizes that are much more manageable, and then we carry out imaging, image reconstruction, and other analyses on these. And these are all sort of computer science questions, data analysis questions. So we have people from those areas as well. Computer vision and machine learning are big contributions to this work. So really, it's just a huge gamut. And if you're interested in any of those areas, right, I highly encourage you to just pursue what you like in them, study them as much as you can, and don't be shy. If you don't have somebody in the collaboration in your local institution, we have a webpage, the eventhorizontelescope.org. Go to it, look at the names of people, email somebody if you have a project in mind or something. the worst that can happen is somebody says no, right? That's really what it is. So I would say reach out. If you have something you really like to pursue and you think you can make contribution, you're in a field, it's an area that you really are working in, and you feel like you're building up your expertise in this area and you'd love to apply it to this project, you can reach out to people individually, and you can keep an eye out for job openings. We have postings in various locations. So there are a few centers, one here at the Harvard-Smitsonian. We have job openings for various areas for this next generation Event Horizon telescope pretty regularly. So right now, I think there are a couple of job openings for a software engineer and for calibration experts. So like, for instance, these sorts of things, we are hiring all the time. And so for students, maybe that's a little bit niche, right? And that's where I would say build up your expertise in your studies and work on projects that interest you. And if this is one of them, try to reach out to people. And you may be pleasantly surprised. We have lots of students in the collaboration who have come from lots of different backgrounds.
Thank you.
Okay. Another technical question. So you said in order to assemble your virtual mirror, you use the rotation of the Earth around its axis. So did you also use the rotation of the Earth around the Sun to make your mirror better, maybe?
This is another excellent question. You think, okay, so as seen by M87, the Earth is rotating, and so the orientations of these various telescopes on the Earth are changing in time. And of course, naturally, the Earth is also going around the Sun. And so the source, M87, if I were sitting at M87, I could also see that. So can we leverage that? Can we use that in some way? And unfortunately, the answer is no, we can't. And the reason is because we need to detect in what we think of as an incident wavefront. We need to basically have all of the light arrive at the same time. So we can combine. So how to say this? We can combine the information from a pair of telescopes that receive light simultaneously. And so that's why, as the Earth rotates, we constantly have pairs of telescopes that are looking at the source at the same time. But if we were to wait for the Earth to move, we have telescopes that are looking at the source now, trying to combine data with telescopes that are looking at the source sometime in the future. And that's not possible. We need to be looking at the same incident wavefront, the same incident photons, in order to be able to pull out the kinds of information that we pull out in interferometry. And I'm sorry that some of this I have to gloss over just why that is, but it turns out that we can't combine information that telescopes take at two different times. We can only combine the information that they take at the same time. So we can't wait for the Earth to move in its orbit because that necessarily requires data taking now and data taking later. Whereas when you wait for the Earth to rotate, you can still have two objects that look at the source at the same time. Does that make sense? Hopefully, yes. Hopefully that made sense. Yeah. So it's a great idea, and it's unfortunately not one we can take advantage of.
Okay. Thank you, Dom. I'll wrap up this session. I'm afraid we don't have much time left. So thank you for your vivid and engaging talk tonight. I felt this hour, I felt it like 20 minutes. It's kind of relativistic effect, which means what? We are very slow.
Too close to a black hole.
To perceive the time to go fast. So it's right, yeah. Okay. Yeah. Thanks again. We wish you success in the future upgrades of the Event Horizon collaboration and whatever you have in front of you in professional and personal life. Thanks again.
Thank you very much. And thank you.
A round of applause for Don.
Take care, everybody.